So good afternoon, participants. So we are starting with our lecture on energy materials, where we are covering materials for batteries. If you remember in the last lecture, we had talked about rechargeable batteries and we had kind of covered lead acid batteries, nickel cadmium batteries, and nickel metal hydride batteries. And then we had moved on to lithium ion batteries. So today we are continuing a little bit on the battery part and going ahead. So for this lecture, what we will be covering is cathode materials for LIBs. Then we'll talk a little bit about anode materials for LIBs. Then how do you characterize a cell, and in which we will be covering particularly for this lecture cyclic voltammetry as well as charging discharging cycles. So this is going to be what we will be covering in the next 90 minutes or so. So coming back to the birth of rechargeable lithium batteries, if you remember, we had said that this entire concept started with the intercalation chemistry. And this intercalation chemistry has been there for a very long time, for almost nearly 180 years. And Schoeffel was the first to show the intercalation of sulfate ions into graphite in 1841. Then Professor Whittingham demonstrated the first rechargeable lithium battery at Exxon Corporation in the United States, and he had used a titanium sulfide cathode, a lithium metal anode, and a liquid electrolyte in which a lithium salt like lithium chlorate was dissolved in an organic solvent, which was glyne and THF, which is tetrahydrofuran. So that was the first battery which was there, and this we had spoken about in the last class, and you saw that there were a little bit of problems in that battery. This work was done, reported in 1976, and there was a little bit of problem in this battery, and the problems were that the cell voltage was limited to less than 2.5 volts. So obviously, since cell voltage is intricately connected with energy density of a particular battery, so obviously this brought down the energy density. And second, and the more important problem was the dendrite growth on lithium metal anodes during cell cycling, which caused internal shorting and presented a fire hazard. So the recyclability of these cells were really compromised because of the formation of these dendritic growth on the lithium metal anodes. So after this, what happened is that instead of the sulfide, what we had was the discovery of the oxide cathodes. So why this oxide cathode? As I said, the cell voltage is determined by the energy difference between the redox energies of the anode and cathode. So the cathode energy should be lying as low as possible and the anode energy should lie as high as possible. So then only you will get a good difference, and that is where your cell voltage is going to increase, which in turn is going to increase your energy density. So if you want a cathode which should lie as low as possible, then the cathode would require stabilization of these higher oxidation states with a lower lying energy band. And the anode, because it has to be as high as possible, the energy of the anode should be as high as possible. In that case, it would require stabilization of a lower oxidation state with higher lying energy bands. So what is the problem? The problem is that whenever you are having a metal ion with very high oxidation state in the metal ion, then this accessing this lower lying energy band becomes a big problem. So then how to achieve that? So when you look into the sulfide, in case of the sulfide, then that is a problem. But the moment you move into oxides, then this becomes much easier. And Professor Goodenough utilized this basic understanding that the top of this sulfide band, it lies at a higher energy than you can see at the top of this oxide band. So he used this concept to design the oxide cathodes. So you see, if you are considering the top of this S2 minus 3p band, then what happens? What happens to your cell voltage when you are putting it versus lithium ion? Then this particular voltage is limited to only this much, which is less than 2.5 volts. But the moment you come to an oxide, you can immediately see the increase in this voltage. So the access to lower lying energy bands with higher oxidation states, like for this cobalt 3 plus 4 plus, and hence higher cell voltage, this is going to be limited. Suppose you take this particular ion also, but this ion, when you are having a sulfide, then its voltage is limited by this top of the sulfide band. Whereas if you move into the top of the oxide band, you have an access to this much amount of voltage. So the top of this O2 minus 2p band, this lies at a lower energy and it enables access to lower lying energy bands with higher oxidation states, and it increases the cell voltage substantially to 4 volts. So from 2.5 volts, you are moving directly to 4 volts and you're increasing this cell voltage. So how do you calculate the theoretical capacity of an electrode material? So this is how we get the specific capacity of an electrode material. So this is given as NF by 3.6 into the molecular weight of materials. So N is what? N over here is the number of reactive electrons per formula unit. M is the molar weight of the materials, and F is the Faraday constant. So the number of electrons, this is correlated with the number of lithium ions accommodated in the host lattice. So in this particular case, when we talk about lithium ion battery, this N value is actually 1. So you have to understand that if you increase N and you decrease M, only in that case you will find an increase in the specific capacity, which in turn is going to increase your energy density. So energy density is definitely a factor of two different things. One is specific capacity and the other is working voltage. So if you are able to increase the specific capacity, or if you're able to increase the working voltage, only then what you will find is the theoretical, the energy density of your material is going to increase, of the battery material is going to increase. So this is a concept which we need to be very clear about.
Ma'am?
Yes?
Ma'am, can you please redefine what capacity, not in the mathematical terms, but in the physical terms, what capacity are we talking about here?
Here we are talking about the capacity means that how much amount of energy is getting delivered. Okay, so what is the energy getting delivered? This capacity is given in terms of milliampere hour per gram. Okay, so how much amount of milliampere hour per gram of the material you are going to get from that particular battery material, that is the capacity of the battery. And we are always trying to get maximum capacity as much as it is possible. Okay, and this specific capacity, as I told you, it plays a very important role in determining your energy density. So if you are able to increase the specific capacity, you increase the energy density of your resultant battery.
So it's like heat capacity, but rather than the heat energy, this is electrical energy.
Yes, of course, it is the electrochemical energy.
Electrochemical energy, okay.
Okay, so this is the idea. So now you have discovery of three classes of oxide cathodes in the 1980s. So right back in 1980s, these three different class of material was discovered, which was used as, which has been used, and still we are using these three different class of materials as cathodes in the lithium ion battery. So one of this is the layered lithium cobalt oxide, which you all know. This came into existence in 1980 when Professor Goodenough came up with this particular cell with lithium cobalt oxide and lithium metal anode. Then there is the spinel LiMn2O4 kind of systems, not exactly this spinel, but your doping and variation of this. So this structure is there, this particular class, so spinel class of materials. And then you have something which is a polyanion. So this is LiX Fe2XO4 thrice, where this X, this higher X, what you see is nothing but a chalcogen molecule. You can have like sulfur, you can also have something like molybdenum, you can also have something like tungsten. So these are different kinds of polyanion compounds which are also used as a class of cathode materials. So layered lithium cobalt oxide, it has an octahedral site lithium ions. So this offers an increase in the cell voltage from less than 2.5 volt, what you saw in titanium sulfide, to for the LiCO2, this increases to 4 volt. And this was very clear from that particular energy level diagram which I had shown in the previous slide. Then in case of spinel LiMn2O4, it has a tetrahedral side lithium ions and it offers an increase in cell voltage from 3 volt for an octahedral side lithium ion with this Mn3 4 plus coupled to 4 volt with an accompanying cost reduction. So what happens is, if this, for this LiMn2O4, what you have is, if you are, this particular Li ion is sitting in a tetrahedral site, and if it is sitting in the tetrahedral site, when it couples with this Mn3 plus 4 plus couple, it gives you a voltage of around 4 volts. So this is also a very big increase. And this, along with it, you're not using cobalt, which is much more expensive. You are using an earth abundant material like manganese. And so there is an accompanying cost reduction also when you're using these kind of spinel compounds. And then you have the third class of compounds, which is a polyanion oxide. As I said, this lithium ferrous sulfate. This is another way to increase the cell voltage, and this is via inductive effect. So from less than 2.5 volt, which you will see in a simple oxide like Fe2O3, if you use a simple oxide like Fe2O3 as a cathode, then the voltage is going to be around less 2.5 volts. But if you are using this kind of polyanion along with it, then you will see that the voltage is going to increase to around 3.6 volts, and there is going to be a further reduction in cost, and there is going to be improved thermal stability and safety. So these are the discovery of the three different classes of the oxide cathode. So now coming a little bit into the details of it. So when you have a layered LiCoO2, please understand this, there is monovalent lithium and there is trivalent cobalt ions, and these are ordered on the alternate 1-1-1 planes of this rock salt structure. You see over here this particular rock salt structure with the cubic close packed arrangement of these oxide ions over here. So this is known as something which is known as the O3 structure. Now, there is a lot of charge and size difference between this lithium and the cobalt ions, and this is going to lead to a very good cation ordering. And this is critical to support the two-dimensional lithium ion diffusion and conductivity in the lithium plane. So if you look into it, this lithium plane, there is the kind of structure what it has, it helps in good diffusion and conductivity. Then with this good cation ordering, what happens is there is direct cobalt-cobalt interaction, if you see, via this edge sharing, whatever is happening. Okay, octahedral edges in the cobalt plane, they are sharing, and so there is a very good electronic conductivity as well. Then when from lithium cobalt oxide, while you are charging it, you are taking out the cobalt and you are storing it in the anode. So then when you are having this Li1 minus X COO2, this becomes more metallic on charging. Why? Because you are introducing holes into the low spin CO3 plus system. So the good structural stability along with high electrical as well as lithium ion conductivity, this offers very fast charge discharge characteristics with very good reversibility, and that is why even today LCO is considered to be one of the best cathode materials to be used in LIB. But there is one problem. The voltage is very high, of course, please remember it is 4 volt, but there is a problem. See, when we talked about the theoretical capacity in that particular formula, where we are having NF by 3.6 m, if you put the m value of LiCO2 over there, what you will find is the practical capacity of this material for one electron transfer, because it is for lithium, you will find that the theoretical specific capacity calculation should come around 274 milliampere hour per gram. But you will find that whenever you are using this particular material, the practical capacity gets limited to around 140 milliampere hours per gram. And the reason is because that if you are taking out the entire amount of lithium from this LiCoO2 while charging, then what happens is then the structure kind of crumbles. So the structure is able to hold itself when you take out around 67% of the lithium from this LCO. So that is why the practical capacity of this material is limited to around 140 milliamperes hour per gram. So now it was not a eureka moment that when I just decided, I saw the periodic table and I came to LiCO2 as a conclusion. It was not that. So when the research on these particular materials started, on this oxide cathode started, so all of these materials were studied, all of them which this LiMnO2 oxides which crystallized in the O3 layered structure, they were all studied. So scandium doesn't form these kind of O3 structure, but titanium, vanadium, chromium, cobalt and nickel, they all form these kind of O3 structures, but they all had some problem or the other which made LCO one of the most superior cathode materials. Why? Because lithium titanium oxide, it operates at a very low voltage of 1.5 volts. So and the synthesis is also not very easy. So that is why this was not really considered, because definitely it is going to bring down the energy density of your battery. Then lithium chromium oxide is difficult to charge. Why? Because it displays a very large polarization with an increase in the charge voltage. So if there's a lot of polarization, that means a lot of overpotential has to be given. So this brings down the efficiency of the battery. So that was also not used. What happened to LiNiO2? It is very difficult to synthesize, and you also have to remember that when you are having LiNiO2, then this Ni has to be in 3 plus form. But Ni doesn't want to be in 3 plus form, it tends to get reduced to Ni2 plus, and if it reduces to Ni2 plus, then automatically some amount of lithium has to come out, so that it cannot sustain the original amount of lithium which was there in LiNiO2. So at high temperature synthesis condition, what happens is some amount of lithium gets volatilized, and obviously if you're having less amount of lithium, in that case there is going to be a problem in your ultimate battery formation. Now when you're having vanadium, manganese and iron, this has another type of problem. That problem is basically that when you're actually moving out the lithium from this structure, then this LiVO2 or LiMnO2, they tend to move from this O3 structure, they will go and form a spinel kind of a structure. So they'll suffer from this layered to spinel transition, or there can be other structural changes. And so obviously what is going to happen is that your structural stability of the material is compromised. So you cannot use it for a long for a battery which has to cycle for a very long duration. And the reason for this is that they have a very low, considerably low octahedral site stabilization energy. You must understand that if the lithium is having a higher, if the octahedral site stabilization energy is more, in that case, what is going to happen? The structural stability is also going to be more. So over here, you see for the cobalt 3 plus, the octahedral site stabilization energy is definitely much more negative than what we see for manganese 3 plus. So this is one of the reason why LiCO2 ended up being one of the very good materials. But at present, you will find that there is a lot of report on, putting in some other material in this LCO kind of material, and that is adding of nickel and manganese. So why do we need to put in nickel and manganese? Why not only cobalt? The reason is because one of the primary reasons is that cobalt is very expensive, and also there are very few mines all over the world which is not equitably distributed also. So to reduce the cost and reduce the dependence on all these other factors, so then the point is that how you can kind of reduce cobalt, but yet you don't compromise on the cathode characteristics of the LIB. So the things which were chosen as good materials to substitute cobalt was nickel and manganese. This definitely brings down the cost and it also increases the capacity. Please understand that in NMC, what is the role of this manganese 3 plus? So when you are using this manganese 3 plus during the synthesis process, it will get oxidized during synthesis and it will form Mn4 plus. Now you are having nickel also in 3 plus form. So what is going to happen? Mn3 plus is going to get oxidized to Mn4 plus, and in the meantime, nickel 3 plus is going to get reduced as nickel 2 plus. And why this is going to happen? Because the manganese 3 4 plus band lies above the nickel 2 plus 3 plus band. So Mn4 plus will help the incorporation of nickel as a stable Ni2 plus into NMC, and this serves as a structural stabilizer without participating in the charge discharge process. So manganese is acting as a structural stability agent in this LiNMC kind of cathode. Another thing is that Mn does not suffer any chemical instability involving oxygen release from the lattice in contrast to cobalt, as the cobalt 3 plus 4 plus band overlaps with the top of the O2 minus 2p band. So manganese doesn't suffer from any chemical instability. So manganese is again also helping in improving the stability of this particular NMC kind of cathode. But one thing is that this Mn, it suffers from structural instability as it can readily migrate from the octahedral site in the transition metal plane to the octahedral site in the lithium plane through a neighboring tetrahedral site. Why? Because it has a smaller octahedral site stabilization energy. So this results in the layer to the spinel transition and accompanying voltage decay during cycling. So that is why only LiMnO2 cannot be used. This is one of the biggest problems because it suffers from structural instability. In contrast to it, cobalt enjoys a good structural stability without such cation migration due to the very high octahedral site stabilization energy, which I had already shown in the previous slide. So now you look into this particular parameters and the trend. So chemical stability, manganese is definitely having much more chemical stability compared to cobalt. Whereas when I talk about structural stability, then cobalt is much more structurally stable compared to that of manganese. Then of course, electrical conductivity, as you can see, is highest for cobalt. Abundance, manganese is the most abundant one. Environmental benignity, again, manganese is the most environmentally benign material. In addition to this above two differences what we discussed, cobalt 3 plus 4 plus, please remember it becomes metallic on charging due to the partially filled T2G orbitals interacting along the shared edges, while Mn4 plus it remains semiconducting. So that is another big factor. And also Mn is abundant and environmentally benign compared to cobalt. So that is why Mn has a lot of advantages when you are reducing a little bit of cobalt and adding in a little bit of manganese to this NMC cathode. Now, in case of nickel, you see all these different parameters, nickel is lying in between manganese and cobalt. And why this is so? Because nickel 3 plus 4 plus band, it barely touches the top of the O2 minus 2p band. So this, if you look into that, the first slide where I had given all these different band structures, if you go back to that, you will find that nickel 3 plus 4 plus band, this is going to barely touch the top of the O2 minus 2p band. So nickel 3 plus can be charged all the way to nickel 4 plus without removal of electron density from the oxide 2p band, and so the loss of oxygen from the lattice doesn't happen. Then Ni3 plus also exhibit an octahedral site stabilization energy value which is intermediate between those of manganese 3 plus and cobalt 3 plus, and so it also offers reasonably good structural stability. Hence, right now what is the trend is that how you can increase a nickel percentage in the NMC cathode, and if you can increase that, then you are actually bringing down the cost even further without compromising on the quality of the cathode material. Now, why
Ma'am,
don't I? Yes.
I have two questions from that slide. If you
Yes.
can please move back to that slide.
Yes.
Yeah, first question is when you are mentioning these T2G orbitals, can you please explain in brief what that is? Because I don't think I've come across that term.
Of course, you have come across it. This T2G orbital is basically from your coordination chemistry concepts. If you remember, you're in coordination chemistry of crystal field theory. So whenever you have a transition metal ion, what happens is in presence of the ligands, it is going to split. Your d orbitals are going to split into T2G and EG levels. For the octahedral one, you have T2G6 and EG2 kind of structures coming in, or X and Y. And then for tetrahedral one, you have E and T2, in which it is getting split. So if you consider CO3 plus, this is basically a D6 system. So if it is a D6 system, in that case, what you will find is basically if the ligand strength is very high, which is in this particular case for the oxide, in that case, this is going to form a T2G6. So it is going to be a low spin complex. So that is the reason why we talk about this T2G level being lying very low.
Okay. And second is in the first point that you have written here, the Ni3 plus 2 4 plus band barely touches.
Yes.
If can you please show on that diagram how we can interpret this, because I'm able to read it and I can see the diagram, but I can't interpret it.
See how this is looking over here. You have Ni3 plus and 4 plus. This is lying above your oxygen tube. It is barely touching it, right?
Right.
Can you
There
see
is a
this Ni3 plus 4 plus? And this is
yeah,
your
there's a very
oxygen
small
2p, 2p level. So this is
yeah.
kind of barely touching it. So what is going to happen is when you are moving from Ni3 plus to Ni4 plus, there is not going to be any concomitant release of oxygen. Whereas when you are doing with CO3 plus to CO4 plus, because these are kind of overlapping, there is going to be an oxygen release. And please remember, if there is an oxygen release, then what is going to happen in your resultant structure? It is basically degrading. So the moment whenever you are cycling this material, so it has to hold in, right? When lithium is moving out and lithium is moving in, it has to hold in that structure. So in between, when all these different processes are taking place, if already your oxygen is moved from the structure, then what you will end up is a structure which is already degraded. So even if the lithium comes back, it cannot sit in its original position. So obviously, because the structure degraded, it's not going to hold on to the specific capacity. And with continuous cycling, your specific capacity is going to go down. So you cannot use that battery for a long cycling process. That is
But
the
in
problem.
that case, we have seen that titanium can also be used, and from the diagram we can see titanium is much above oxygen, then it should be even better at that.
No, but if titanium is above that, then what is the problem with titanium? This is what I explained. If you are having titanium 3 plus, 4 plus is sitting over there, then what is its voltage compared to lithium, lithium plus? That voltage is
Okay,
again very less.
very less. So
Yeah. So that is the reason why this is the problem over here. So as I have mentioned over here, if you look into this particular diagram, this LiTiO2 operates at a much lower voltage. So that is why
okay,
you
right.
cannot consider that, because the energy density then becomes very less.
So we have to optimize for all these factors all at once.
Yes, yes, that is precisely the reason why that choice of that electrode material and how you will find out, this is very important.
So is there a hierarchy of these factors that we consider? Like this particular factor is the most important, then this one comes next.
No, the what is paramount is, see here basically your end will show your means. At the end, what you need is something which should give you a higher energy density and for a very high cyclability. You have to consider some important factors for a battery to material. One is energy density, the other is cost, the other is your availability of the materials. But the paramount factor is your energy density and the cyclability. That is very important. If you have a good, very good material, but it is cycling only for maybe 50 cycles or 100 cycles, that is definitely not a good rechargeable battery. So you have to go at least beyond 5,000 cycles. So then only you
So
will consider that this battery is good. So energy density and cyclability is definitely one of the primary factors. Its rate capability is another very important factor. that how fast charging discharging it can it can withstand. So those are all different factors. So now with this end in mind, now you have to find out that what are the materials which is going to give me this end result. So
So
that
we
is
need
the
some. So we need something that when the ion leaves the whole lattice,
yes,
uh, the structure is not distorted or crumbled a lot, right?
right, right.
So in that case, as the first ma'am had taught us about, why don't we use perovskites for that? Because they are more resistant to this sort of
Yes,
distortions.
those are the new generation materials which are coming in. But for the perovskites also there are certain problems which we will again discuss in the coming slides.
Oh,
So
we'll
all
be
these
discussing.
new,
Okay.
yeah, so new materials are coming in. So we will also talk about why perovskites. A little bit we'll touch upon that also. What are the new materials which we are getting studied right now? Okay. So here
Okay,
we
ma'am.
are giving it a more common, for the betterment of all the participants. We are discussing the common materials which are being used, not really moving it, because various type of materials are being tested both as cathodes and anodes. There is endless amount, but none of them is as of now giving any competition to all these two materials whatever is being developed for the commercial lithium ion battery. Okay, one is LCO and the other is this NMC, and later on you will find this LiFePO4, these kind of materials. Okay, so
Okay.
I'll just
Thank you.
continue with the class. Yeah. So now, so you see, nickel 3 plus exhibits an octahedral site stabilization energy value, which is intermediate between those of Mn3 plus and CO3 plus, and this is offering reasonably very good structural stability. So that is why right now the idea is how we can get a nickel-rich NMC cathode. Okay, so that is the idea. Then we were talking about the problems which are associated with only LiNiO2. As I said, Ni in this LiNiO2, what is going to happen? Ni is going to be in 3 plus form, and it doesn't support itself in 3 plus form. This will come from your coordination chemistry knowledge. Why it doesn't support itself in Ni 3 plus form? It has a tendency to reduce to Ni 2 plus, and the moment it reduces over there, it will lose some part of the lithium. So what will happen? There is going to be a cation disorder between lithium and nickel, because there will be now nickel present in the lithium layer, and now this is going to impede your rate capability. And rate capability is the factor. What is the rate capability? That if you keep on increasing the current, how fast the charge discharge cycle of your battery is happening. So that also we'll discuss in the later slide. So now LiNO2, another problem is that it undergoes a series of phase transitions during the charge discharge process, particularly at deep charge, involving removal of significant amount of lithium from the lattice. So this will again lead to degradation, and there is going to be a lot of structural degradation, which is going to degrade your rate capability also, because when there is a deep charge, there is removal of significant amount of lithium. And also Ni4 plus, when it forms, it is highly oxidizing. When it will form Ni4 plus, when you have taken out the entire lithium from LiNiO2, what you are left with is Ni4 plus. And this is highly oxidizing, and it is going to react aggressively with all the organic electrolytes which are used in lithium ion cells. And what the result will be, you will form a very thick SEI layer, which again will degrade the rate capability. It will increase the resistance or the impedance, and it is going to consume active lithium. So these are the problems. So that is why we cannot use only LiNiO2. So my thing is that I cannot use only LiMNO2 because there are some problems associated with it, though it has some good factors also. Similarly, I cannot use only LiNiO2 also, because these are the problems associated with LiNiO2. And that is why what I am doing is LiCO2 functions very well, but it has a higher cost. So what I am doing is I'm trying to take in a little bit of Ni and some Mn, and I'm trying to improve the capacity of this NMC type of cathodes, making it even better functioning compared to that of LCO. So another problem is that the chemical instability of this highly oxidized Ni4 plus, what it will do is it will result in transformation of this LiNiO2 to a layered oxide, to a rock salt kind of phase. This is LiX Ni1 minus XO. This is a rock salt phase on the surface of LiNiO2. So what happens is that once this particular phase is formed, then it is not going to function as well as the LiNiO2, and this is also going to degrade. So there's a structural degradation again happening. So again, the highly oxidized and unstable Ni4 plus will also result in thermal runaway. So these are these 5 different problems which are associated with LiNiO2. So what is the push? The push is that you have to increase the energy density. So what you have to do is you need to kind of find out what is the ideal composition of this NMC. So how much amount of Ni can I actually push in? How much Mn should be there to support the structure? And how much of cobalt I can reduce in LCU. So all this research right now which is going on these NMC materials, you'll find it is dedicated to this particular effort. So we'll have an outlook on these NMC cathodes. So layered oxides with high nickel contents, they have these three critical challenges, as I said. One is the cycle instability, another is the thermal instability, and third one is the air instability. And this is related to the instability of nickel 3 plus or nickel 4 plus in contact with the liquid organic electrolyte or ambient air. So the chemically unstable this nickel 4 plus, which is generated on this charged layered oxide material with high nickel content, they will react aggressively with the electrolyte, and it is going to form a very thick SEI along with dissolution of nickel and manganese. And what this nickel and manganese is going to do, it is going to move from this cathode and it's going and sitting and making itself very comfortable on your anode material. So the moment there is going to be this transition metal deposition of your graphite anode, it is going to again catalyze electrolyte decomposition in the anode layer also. And there also you will find a very thick SEI layer forming with a multi-layer structure. And this is going to increase with the increasing number of cycles as more and more transition metal ions dissolve and migrate to the anode. So at the end of the day, what is happening? Your SEI layer is getting thicker and thicker. You are losing more and more amount of lithium. So what happens? So if you look into this particular thing, from the cathode, you see the movement of this transition metal ion. You also see this lithium ions also moving. So what is happening on the graphite when you have this SEI layer formation? You have something which is transition metal and fluoride, enriched. Why fluoride? Because you are having PVDF, you're also having PVDF, which is the binder material which is used. You're also having this Li PF6, which is being there as the salt material in your electrolyte. Then you have something which is now oxygen enriched. You also have something which is lithium enriched. So at the end of the day, the problem is that your SEI is getting thicker and thicker, and then it is going to show up as introduce cracks with new surfaces on cycling, which will again aggravate the surface reactivity with the electrolyte, and it will keep on forming this SEI. And the moment more and more SEI keeps forming without stabilizing, you are losing more and more lithium. Your capacity is continuously decreasing, and this is not a cyclable material. So that is why you have to be very, very careful about when you are using this NMC cathode, that how much amount of it, how much amount of nickel, how much amount of manganese, and how much amount of cobalt you can use. So what are the methods which are being taken to prevent this? So all these different challenges which we have. So one of it is bulk cation doping, as well as you stabilize this surface. So many times you will find right now you will have different cathode materials on which there is a surface passivation happening, but the surface passivation is such a way that it is not going to allow your these transition metal ions to dissolve and move into your electrolyte and then go and deposit itself in the anode. So what you do is substitute this transition metal ions with a small amount of inert ion like aluminium. So you see over here, what you had is all these transition metal ions which are blue in color, and over here instead of that you have put in an aluminium ion. So what is going to happen? This aluminium ion is going to bind very strongly with the oxygen. So this drastically it is going to suppress the metal ion dissolution from the cathode. Why? Because the covalent aluminum oxide bond, it will keep the oxygen tightly bonded. It is going to lower the basicity, and it is going to discourage the transition metal ion dissolution by acidic attack. So that is why you have now this NMCA cathode, where A stands for aluminum. So that was all about your LCO kind of cathode materials. Now coming to the second class of cathode material, which are basically your spinel oxides. So in the spinel, this is NiMn2O4, this Mn3 plus 4 plus ions, they occupy the octahedral sites, and the lithium ions, they are occupying the tetrahedral site. Okay. So what happens is the stable, this Mn2O4 framework, it has an edge-shared octahedra which offers a three-dimensional lithium-ion diffusion pathway. So you see this is a three-dimensional lithium-ion diffusion pathway over here, and so it will give a very fast lithium-ion conductivity. Whereas in case of LCO, it was a two-dimensional pathway. Here it is a three-dimensional pathway. And there is also direct MN-MN interaction, which you found in the LiCO2 also. There was a direct CO-CO interaction, but here also you have a direct MN-MN interaction across this shared MnO6 octahedral edges. And what is going to happen is this facilitates a very good hopping electronic conduction. However, because of this Mn structure, it remains as a small polar-ion semiconductor during the discharge process. Whereas, if you remember for LCO, I said that it becomes more and more metallic. So the insertion and extraction of lithium into and from these tetrahedral sites with deep site energy in LiMn2O4, they offer a higher operating voltage of 4 volt with a practical capacity of less than 130 milliampere hour per gram, as close to, because this is why, because with every two manganese ions you can you can move one lithium ion. It can be reversibly extracted from the tetrahedral sites. So you see the lithium diffusion pathway over here. If you see that there is a particular vacancy over here, and basically this lithium ion is hopping through that, and you're having a two-dimensional pathway. Whereas when you are looking into these kind of spinel structures, there is a vacancy over here, and this lithium ion is moving through this neighboring empty, this 16C octahedral site in the spinel cathode, and that is why it is having a three-dimensional channel to move. So that is why the lithium diffusion pathways are better in case of a spinel oxide. So it is good. So lithium diffusion kinetics is very good. So this is a good material. So what is the problem? Now the problem lies is the dissolution of manganese from the lattice into the electrolyte. Whenever there is a trace amount of hydrogen ions in the electrolyte, why? Because there is going to be a disproportionate reaction. So your Mn3 plus is going to disproportionate into Mn4 plus and Mn2 plus in the presence of any kind of acidic any little amount of acidic nature in the media. And during this disproportionation, what is going to happen? Mn4 plus stays in the solid, but Mn2 plus get leached out into the solution. So what is going to happen now? It is going to degrade the cathode because it has disproportionated. It is Mn4 plus is staying in the cathode, but Mn2 plus is leaching out into the solution, and it will migrate to the anode, and it is going to poison the graphite anode, and it's going to limit the cycle life of your lithium ion. So, but it has been seen in research that if you are substituting a small amount of lithium for manganese in this, it perturbs the long range manganese interaction or contact, and it kind of frustrates this Mn3 plus disproportionation reaction, and it reduces the dissolution, and that is why it improves the cyclability of the material. So if you are doping a little bit of lithium, the extra lithium, if you are putting it in this LiMn2O4, then you know the cyclability is going to kind of improve. Now, the same way, if you are talking about manganese, so let's see what are the other spinel structures which is supported by all these different transition metal ions. And you see that there is titanium, which is can be a candidate, vanadium can be a candidate, and also you can, it is only titanium and vanadium which can act as a candidate over here. Again, for titanium, the main problem is it operates around 1.5 volt, low voltage, low energy density, so it is not a suitable cathode. And lithium vanadate, on the other side, it suffers from structural changes, and the voltage is also lower. In this case, it is for manganese, it is 4 volt, but for vanadium, it is around 3 volt. So obviously, if I want to really work into spinel oxides, I will look for manganese materials. Then the third class of material, which is the polyanion oxides. Now look, this is something very interesting. You have some lithium plus, which is acting as your anode material. For any half cell, whenever I have any new material which I need to test, I will test it versus lithium ion first. And then after that, when I find that it is a good cathode material, then I'm going to put it with my anode material and prepare a full cell. So whenever I'm testing any material, it is versus lithium ion, and that is known as a half cell testing when we talk about the coin cells. So now we look into this particular very interesting structure over here. You have Fe2 plus 3 plus. Okay, so this is the band structure of it. When you have Fe2 3, you look where the band is, and when you have this Fe2 SO4 thrice, this is also again Fe2 plus 3 plus system, but see the voltage difference. So from Fe23, which is Fe2O3, which is less than 2.5 volts, when you are going to molybdate, it is around 3 volt, and when you are going to the sulfate, it is around 3.6 volt. So obviously you can see lithium versus lithium to lithium plus, you see how this voltage is increasing. And obviously I know if my voltage is increasing, then this is going to be a good cathode material, provided all the other factors are taken into consideration. So this means what? This means that your whatever is the counter anion is again playing a very important role. So what is this? So you have this XO4 tetrad, where what is X? X can be your molybdenum, it can be sulfur, it can be tungsten. So this is providing an extended three-dimensional OFeOXO kind of linkage. So as a result, the more covalent this MO bond or tungsten oxide bond or sulfur oxide bond, this weakens this iron oxide bond covalency through inductive effect compared to that of the simple oxide. So this results in the lowering of this Fe2 plus Fe3 plus redox energy, and so there is a consequent increase in the operating voltage. So from less than 2.5, I am moving to 3.6 volt. And this is not the only thing. I am also using very earth abundant materials like iron over here. So obviously this is going to be another very good class of oxide materials. So as I said over here, Fe2 plus 3 plus, if you see if it's a free ion, in that case all the d orbitals are basically on the same level, but the moment you're having a ligand, then there is going to be a splitting happening. So for a molybdate, the splitting is going to look like this, whereas in case of a sulfate, the splitting is going to look like this, depending on the inductive effect of this counter anion. And as you can see, your voltage is increasing. So from 3 volt, which is in case of a molybdate, for a sulfate it is increasing up to 3.6 volts. So from this particular idea came in the idea of this other very important cathode material, which is made of earth abundant materials. Instead of SCO, you'll have LiFePO4, and this was the olivine LiFePO4 material, and this was identified as a good cathode material in 1997. So this increases the ability to increase the voltage drastically to as high as 5 volt in polyanion cathodes. For example, in this, and even with lower valent couples, like you can also use cobalt 2 plus 3 plus or Ni2 plus 3 plus. So this power of the inductive effect, it becomes very, very strong in this case. So you have these different kinds of appealing cathode materials which has been developed for lithium ion batteries. So this is lithium vanadium phosphate, you have sodium vanadium phosphate, you have sodium vanadium fluorophosphate. All of these have become very appealing cathodes for lithium as well as sodium ion batteries. So what are these advantages and disadvantages of the oxide cathodes? So for the layered and the spinel oxides, it has good electronic conductivity. Polyanion oxides suffer from poor electronic conductivity. This has a very good close pack structure with high density. Here the structure has a lower density. This is a very high volumetric density, where this has a low volumetric density. So what essentially this means? That if I am looking for something which is going to have a good energy density, you need something for a very high energy density, maybe for portable electronics and all, then probably LCO is going to be a good cathode material. Whereas polyanion oxide can play a good role where energy density doesn't play that much amount of a big role. So for renewable energy storage, where the space is not a matter, then probably you can use this kind of LiFePO4 material as a cathode material for those kind of storage batteries. And this electronic conductivity is taken care of by adding in a little amount of conductive carbon, so that the conductivity part can be taken care of in case of these polyanion oxides. Now coming to the anode part.
Excuse me, ma'am.
Yes.
Sorry for interrupting again, but I have a question about the layered one.
Yes.
Uh, yeah, we have here that it's good electronic conductivity as well as high density. So
Yes.
doesn't it run the risk of having chances of electronic runaway, like runaway currents or thermal runaways?
See, in your battery material, you must understand what is happening. In the battery material, you are having your electrolyte and your separator. Both of it are basically ion conducting, but it cannot conduct electrons. So electrons has to go in through the external circuit. Okay. So inside your battery material, the electron movement is always happening outside, the ion movement is happening inside. So your
Okay.
electrolyte material is ion conducting, but it shouldn't be conducting electrons. Similarly, your separator material should be permeable to the ions, but it cannot it shouldn't be something which is allowing any electron to pass. So electrons has to move in through the external circuit.
Okay. Okay.
Okay.
Okay.
So now coming to the anode materials. See, anode materials, as I said, lithium plus is definitely one of the best anodes. Why it is the best anode? Because you see the tremendous amount of energy density lithium metal ion, when you are having that particular as an anode material, is going to have. It's very high energy density. So the idea for all the electrochemical, researchers is that I should have lithium plus. But what is the problem? The problem is, as I mentioned before, that it's very difficult to stop that dendrite formation, and definitely that gives rise to a lot of safety concerns, because if there is a dendrite formation, it's going to perforate your separator. It is so there's going to be short circuit happening, because and from the anode this dendrite is going to form and is going to come and touch the cathode material, and then obviously if there's a short circuit, your battery doesn't work. So we need a safer material, and that safer material is basically what is that? That is basically your carbon. Why? Because the operating voltage of that is very close to that of lithium plus. Lithium plus is zero. So in that case, what we are having is around 0.1 volt, which is as close as that you can get to lithium plus. And what does the carbon do? For each 6 carbons, I have one lithium ion intercalated in it. So this gives a good, reasonably good energy density of around, theoretical energy density of around, or capacity, specific capacity of around 372 ampere hours per kg, which is good enough. And that is why for all the commercial ion batteries, we are using carbon or graphite, you can say, as the anode material. So please understand that although the redox energy of this graphite, it lies above, you look where graphite is and where the lowest unoccupied molecular orbital of, or the electrolyte, whatever electrolyte we are using right now, which is the carbonate solvents, and the salt is LiPF6. You see, this graphite is actually lying above the LUMO of the organic electrolyte. So it will form this solid electrolyte interface. And the formation is very important, as I told you, SEI formation is important because this is kind of passivating that particular anode, but it is not stopping your lithium ions to pass through it. But what it is stopping is further disintegration of your electrolyte by reaction with the lithium, whatever is there in that anode material. So that is very important. Okay. So what happens is, this is what I have written over here. The formation of a stable solid electrolyte interface layer on the graphite surface in reaction with electrolyte solvents provides the stability for its operation for a very long time. Okay. So now, apart from this graphite, which you sit over here, which is sitting over here, if you see the voltage and the capacity, this graphite is somewhere over here, 372. You also have a few other anode materials to consider. One is, this spinel structure, this lithium titanate. You see over here what is happening. This is lying in between the HOMO and LUMO of your electrolyte window. So this will not give rise to formation of any SEI. And without the formation of SEI also, there is very negligible volume change. But why am I not using this as an anode material? Because you look into the capacity. In this case, the capacity is very low. Obviously, why? Because the molecular weight of this material is quite high. So though it doesn't form any SEI, so your energy efficiency of this material is going to be very good. So the Coulombic efficiency is going to improve. But what is going to happen is the capacity is going to be low. So that is why, though it is used, but it is not definitely in the commercial level. So the operating voltage is 1.5 volt versus lithium plus, and there is a limited capacity. So it reduces the cell energy density drastically. However, this lithium titanate, it can be employed in cells for grid storage. So what is the effect of structure on the electrochemical potential of electrodes? So generally what we do is we generally have lower size, smaller size. So why we look into nano forms? Because if you are having material which is a very small size, these cathodes and anodes, very small size, then what is going to happen? There is going to be an enhancement of the reversibility of the lithium ion insertion and extraction reaction in these nanostructured electrodes without destroying the crystal structure. Then obviously there is going to be a reduction in the diffusion and the transport distance of the lithium ions and the electrons accompanying the lithium ion insertion and the extraction reactions. And also there is going to be a change in the site energy of lithium ions occupying the host lattice, which is going to affect the electrochemical potential of the electrodes. So these are the benefits when you are using the nanostructured form. Then what is the effect of defects on the electrochemical potential of electrons? How do you introduce defects? You can introduce it to the doping in your whatever material you are using. How do you introduce defects? It can be through doping. It can be through treatment, different kinds of atmospheric treatment you are doing. You can control the synthesis method. So now if you look into this particular plot, this is basically a specific capacity, and on the y-axis what you're having is your potential versus lithium ion. So the original material which was used is vanadium oxide. Okay, and now you have doped some nickel in this vanadium oxide. So if you are having only vanadium oxide, you see the specific capacity. So this discharge capacity of it is around 225 plus minus some delta. But the moment you are kind of doping it with nickel, you see the specific capacity is increasing to almost 270 milliampere hour per gram. So what is happening? The lower valence of nickel in place of this high valence vanadium in V2O5, it effectively decreases the electrostatic repulsion between the cations, and thus it decreases the lithium site energy, and so it increases the potential of the doped material. So that is why your specific capacity of this is increasing, because it is decreasing the lithium site energy. Then effect of amorphous state on the electrochemical potential of electrodes. So mesoporous amorphous materials, they are conducive to the full infiltration of the electrolyte, which reduces the migrating distance. So you please imagine what is happening. For an amorphous material, the electrolyte is infiltrating right inside it. So that exchange is happening very nicely over there. So this facilitates the lithium ion exchange across the interfaces, and it can tolerate large volume changes of the electrodes during this lithium ion insertion and extraction. But what is going to be the natural pitfall of this? If I am really taking an extremely nanomaterial as my electrode, the problem is going to be that if your electrolyte is infiltrating it this much, then for every portion where your electrolyte is infiltrating that electrode, you are going to form an SEI. So the amount of the SEI formed is going to be much higher. If that is the case, then your efficiency is decreasing, because more amount of SEI form means more amount of lithium is not getting back into the reversible charge discharge reaction. So more and more amount of the lithium is getting lost. So that is why your specific capacity is going to decrease, and so your coulombic efficiency is going to be much less. So again, you have to play a balance that how much of size reduction you will do to ensure that your SEI is formed, but then your coulombic efficiency is not compromised to a large extent. So what is the current status of LIB? This is very important. So what you have is commercial lithium-ion technology is largely limited to cells with gravimetric energy densities at present is around 250 watt-hour per kg, and the volumetric energy density is around 650 watt-hours per liter. But the target is this, so we need to move up to this target, and obviously for that you need to, as I said, if you have to go up to that much amount of energy density, there are two areas where you have to play. You can increase the cell voltage or you increase the capacity. So the only option to increase the cell voltage is raising the operating voltage of the cathode, as the graphite anode operating voltage is already close to that of Li plus. You cannot decrease the voltage any further, because it's almost 0.1 volt only. How further can you decrease? Not much idea. So only thing is that you can increase the voltage of the cathode. Now you do get many materials with a higher voltage. Look into this, like if you are replacing nickel in place of manganese in this spinel cathode, you can go up to 4.7 volt almost. If you are taking LiCoPO4, in that case it is 4.8 volt. So you can have very high voltage, but what is the limiting factor? It is the electrolyte. The homo nouveau level of the electrolyte, we are not able to get good electrolytes which is going to sustain that much amount of difference. Otherwise it's going to be there's going to be a lot of SEI formation, and your material is not going to be that good. Your battery is not going to work very nicely. So that is the way. So one is that cell voltage. You had some question?
Yeah, I have one question.
Yes.
You mentioned that most we can go up to like 4.3 or little above that.
Yes.
But for example, the battery on my laptop, it charges at 3.1 something amperes at 20 volts.
Hmm.
Like the output from the charging brick, that is 20 volts.
Hmm.
So what kind of material can charge up to that high level of
See, now
voltage?
that is another separate part. So that is your charging and discharging. Okay, so you can have a constant current, you can have a constant voltage. So that is again different thing. This is basically we are talking about the half cells. Right now, what we are talking about is the half cell in the half cell form versus lithium plus. How much amount of voltage it is going to give you? But what you are talking about is the rate capability. Okay,
Okay.
so that is another different story. So that we will come to. So that full cell again, we'll tell you that how basically that rate capability is happening. Why 20 volt? That 20 volt, your material is not going to sustain the 20 volts over there. Okay, so what is that? Inherent voltage is different. So this particular material, when it is working, it is different. So that we will come to. So when you are having that coin cell, how you are charging or discharging the battery, what is the rate capability? That is very important. That is telling you how fast it is charging. Okay, how much the discharge and charging is happening, how fast it is happening with a higher current rate, that is what it is showing. So that we will come to.
Okay, ma'am.
Okay. So now you have something which is known as, this is when you're increasing the cell voltage, that is one way you increase the energy density of your material. And another is you increase the charge storage capacity. So please understand the capacity of this insertion reaction electrodes is limited by the number of crystallographic sites which is available for the reversible insertion extraction of lithium. When you are having a conversion reaction electrode, you don't have such limitations. So what do you exactly mean by this? Charge storage capacity, for you to please go back to your theoretical specific capacity calculation. If you remember, it was NF by 3.6 M. So that n value, if you are increasing, so how do you increase that n value, the number of electrons which is getting transferred? For that, basically, you have different categories of these electrode, of these anode materials, whichever is there, or the cathode materials, whatever is there. So you increase the n value, and that you can increase by using system which is known as conversion reaction anodes. So instead of intercalation, which is the carbonaceous anodes, you can also have materials which undergo conversion. You can have materials which undergo alloying. So if there is alloying happening, then lots of lithium is getting intercalated, in a single molecule. So you have like if I am using bismuth, I have Bi3 Li kind of, these are the different kinds of alloys which are getting formed. So if you use those kind of materials as anodes, then you can improve the capacity like anything. So at the end of the day, what are the things which has already been tried is that you reduce the particle size to nano size, or you deliberately leave space within the active material architecture. So what happens is you are increasing the SEI formation and you're decreasing the volumetric energy density. So this is the pitfall of that. So the only progress which has been seen so far is incorporating a few percent of silicon into graphite to increase the charge storage capacity marginally in the practical cells. So when you look into the research work being done, so many different materials are coming in, but as of now, very few are able to actually nudge the workhorse over here, which is basically graphite materials. So where is this technology headed now? So we can say that this insertion reaction cathodes and anodes will continue. Whatever, this insertion reaction cathodes and anodes, this is going to continue for foreseeable future despite their limited energy density, which is dictated by the number of crystallographic sites available as well as the structural and chemical instabilities at deep charge. And much effort are being made towards conversion reaction anodes and cathodes, as they offer up to an order of magnitude higher capacities than insertion reaction electrodes, but their practical viability is met with challenges. And of course, you have a lot of renewed interest in employing lithium metal as an anode and replacing this liquid electrolyte with a solid electrolyte. But still a lot of research has to go in this field. So as of now, the feasible near-term strategy is to focus on this high nickel layered oxide cathodes, liquid electrolytes which is compatible with and forming stable SEI on both graphite anode as well as this high nickel cathodes. You can have innovations in cell engineering to fabricate thicker electrodes and reduce the inactive components, because whenever you're preparing these electrodes, you're not only using active material, you're using a binder, you're using a conductive material like carbon. So these are all inactive components. So they bring up the weight of your electrode, but they are not contributing to the electrochemical reaction. So if you bring down the inactive components, you increase the energy density of your battery. And you have the novel system integration to realize safer, long life and affordable systems. So you see what are the different kinds of materials which you can use. Usually this is what we are using right now. This is the insertion kind of materials. Lithium inserted into cobalt oxide layer, lithium inserted into graphite. So this is what we are using. So this is kind of commercialized. Then what you have is alloying kind of material. So this has very large capacity, but the volume change are still an issue. And conversion materials, you can see this is under development. This is large capacity, but this has lot of voltage hysteresis. So right now we are still over here, which is commercialized. We are working on this, and this definitely is under development. So this is where the lithium-ion technology is headed, and parameters that need to be considered in adopting lithium-ion batteries for various applications. Definitely energy density, as you said, that what are the parameters I should be looking in. I had a question. So this energy density is important when you talk about electric vehicles, when you talk about portable electronics. Whereas for grid energy storage, energy density is not that very important, but what you need to know is cost, its cycle life, its safety. Those are again points to be considered when you talk about grid energy storage. But please remember, it is desirable to have a fast charge discharge rate for all three applications, and this is where all your that voltage and your markings are all coming into picture. So now this was for electrode materials. Now we move into something which is the cell characterization. For cell characterization, what we use is CV or cyclic voltammetry. So cyclic voltammetry, I will just tell you that this is commonly employed to investigate the reduction and oxidation processes of molecular species. So now there are two different, you'll find that CV plot looks like this. So one is for the oxidation, the other is for the reduction. So when we talk about the IUPAC convention, this is basically oxidation is on the top part and the bottom part is reduction. So you're moving from high potential to low potential. Whereas in US convention, in many of the bigs, you'll find this, there is a confusion between this. So in the US convention, you are putting in the high potential here and the low potential over there. So this is what happens. You are moving from here, the reduction happens, and then you go to oxidation. The same thing, but only the convention in which it is shown is a little bit different. So this is basically cyclic voltammetry using a very simple example, just for those who are not really up to the mark with cyclic voltammetry. These few slides are there, some 4 or 5 slides are there to make you understand the process. So suppose we are considering the reduction of this ferrocenium ion via this cyclopentadiene ion. This is this FeCP2 plus, CP2 plus, and this is abbreviated FC plus over here. So this is adding in an electron, and what is forming is FC, and this is what we are kind of monitoring over here. So what you are having is the concentration, where blue one is basically your concentration of FC plus, whereas the green one is your concentration of FC. And if you are seeing in all these different points A, B, C, D, E, F, G, you are seeing how basically you are gradually you are forming FC. The concentration is increasing as the distance from your, this D is from the electrode surface to the bulk solution, what is the distance. So this is what you are kind of assessing, and this is your final current versus potential plot, what you will be seeing over here. So this is how it looks. So you are having this, if you look over here, what is this convention which has been used? You are having higher potential here and lower potential here. So for this particular plot, this is the US convention which is being used. So the reduction is happening here, the oxidation is happening there on the bottom side. So why are these peaks there in the cyclic voltammogram? Because there is equilibrium between this Fc plus and Fc, and this is described by the Nernst equation. So you have this Nernst equation over here, E is equal to E0 RT by NF ln the concentration of your oxidant by the concentration of your reductant. And when you are talking about one electron reduction, these activities of this are replaced by the concentrations, which is more experimentally accessible. So you have this standard potential being replaced with a formal potential, n is set to 1, and so ultimately what you have is this particular equation. So when the potential is scanned during the CV experiment, the concentration of the species in solution near the electrode changes over time in accordance with this Nernst equation. So ultimately what you are having over here, so there is an increase in the current till point C, and after that you find this decrease happening. Why? Because more and more the volume of the solution at the surface of the electrode containing the reduced species called the diffusion layer, it continues to go throughout the scan. So this will slow down the mass transport of this Fc plus ions to the electrode. So thus upon scanning to more negative potential, the rate of diffusion of these Fc ions from the bulk solution to the electrode surface will become slower, and that is why you will see this particular decrease in the current as the scan continues from C to D, and the reverse process is going to follow. So what we have over here is basically a point where your reduction is happening and a point where your oxidation is happening, and these two peaks are separated due to diffusion of the analyte to and from the electrode. So now if the reduction process is chemically and electrochemically reversible, then the difference between the anodic and cathodic peak potential, which is known as the peak-to-peak separation, delta EP, is 57 millivolts at 25 degrees centigrade. And the width at the half max on this forward scan of the peak is 59 millivolts. This you can calculate from the Nernst equation. And when there is a low barrier to electron transfer, so when there is an electrochemical reversibility, this Nernstian equilibrium is established immediately upon any change in the applied potential. Whereas when there is a high barrier to this electron transfer, so that means there is an electrochemical irreversibility, then these electron transfer reactions become very sluggish and more negative potentials are required to observe reduction or oxidation reactions, negative or positive potentials as the case is, and this gives rise to a very large separation, peak to peak separation. So here the scan rate is very important. So when you are actually recording a CV, the scan rate is very important. So this controls how fast the applied potential is scanned. So faster scan will lead to a decrease in the size of the diffusion layer, and as a consequence what you will see is you will see much higher current. And this is given by this Randall-Sevick equation. You can see this IP, or the current which you observe over here. For an electrochemically reversible electron transfer process which involves freely diffusing redox species, you have this particular equation, and this describes how the peak current, this is IPA, it increases linearly with the square root of this scan rate, which is this nu, which is volt per second. All these other factors are explained over here. You can see where n is the number of electrons transferred, and also A is the electrode surface area. This is the geometric surface area. D is the diffusion coefficient, and CV is the bulk concentration of the analyte. So with this, you can find out what is going to be this peak current. Now, if you have an electrode adsorb system, this is 3 electrode system. So there are many things which are there over here. In this particular case, the current response for an adsorbed species is expected to vary linearly with this scan rate, this new value. So for an electrochemical quasi-reversible process, the peak-to-peak separation shifts with the scan rate, while for a surface adsorbed species, there is no peak-to-peak separation is observed. So please understand the electrolyte is made of a solvent. You have a solvent and then you have some ions in it. So what is that solvent? This has to be liquid at experimental temperature. It should dissolve the analyte and high concentrations of the supporting electrolyte completely. It should be stable towards oxidation and reduction in the potential range of the experiment. It should not lead to deleterious reaction with the analyte or supporting electrolyte, and it can be purified. So those are the characteristics of the solvent which you use for the electrolyte. So you have to check the electroactive window also. So this is all influenced by the electrolyte as well as by the electrode as well as by the solvent. You can see all these different materials which are using, which is kind of giving you different potential window or electroactive window. So accordingly, you have to check the electrolyte characteristics also, just like you check for the solvent. So it should be highly soluble in the solvent chosen. It should be chemically as well as electrochemically inert in the condition of the experiments, and it should be purified. It can be purified. So large supporting electrolyte concentrations, this is going to be necessary to increase the solution conductivity. And as the electron transfer occurs in the electrodes, the supporting electrolyte is going to migrate to balance the charge and complete this electrical circuit. The conductivity of the solution is dependent on the concentration of the dissolved salt, and without the electrolyte available to achieve charge balance, the solution will be resistive to charge transfer. So these are the points you have to remember when you are doing a normal 3 electrode kind of electrochemical reaction. So the movement of the analyte also happens. It is not the electrolyte ions only moving. The analyte ion can also move, and if that moves, then there is going to be a problem. So what are the types of movement which is there? It can be convection, migration, or diffusion. So generally convection you reduce by absence of any stirring or vibration. Migration is minimized through the use of electrolyte in high concentration, and diffusion also you can minimize. So you use a high electrolyte concentration relative to the analyte concentration. So you ensure that it is statistically more probable that the electrolyte will migrate to the electrode surface for the charge balance. So please remember that whenever you do any kind of modeling or theoretical treatment, you will exclude this migration and convection, and you are actually calculating all this diffusion. So convection and migration is considered to be negligible. Now you have something which is known as a working electrode. So you have your performing electrode, your working electrode, you have a counter electrode. So working electrode is the one which is basically where your electrochemical event of interest is happening. And what you do is the potential stat is used to control the applied potential of the working electrode. This is as a function of the reference electrode potential. And the most important aspect of this working electrode is it is composed of redox inert material in the potential range of interest. And the type of working electrode can be varied from experiment to experiment to provide different potential windows or to reduce or promote surface adsorption of the species of interest. So this is just a small side note which has been given to show you how to polish a glassy carbon electrode when you are using one. Then you have something which is known as the reference electrode. So anything, whatever you are measuring, it has to be reference to some electrode, and the reference electrode is used for that purpose. So this is used as a reference point against which the potential of this electrode can be measured in an electrochemical cell, and the applied potential is thus typically reported versus a specific reference. So you can have these different kinds of reference electrode, and then what you have is the counter electrode. So when a potential is applied to the working electrode such that reduction or oxidation of the analyte occurs, then the current will begin to flow. What is the purpose of the current counter electrode? It is to complete that electrical circuit. So you have to ensure that the current is recorded as electron flow between the working electrode and the counter electrode. So normally what you are using is a platinum wire or disc, which is used as a counter electrode. Sometimes carbon based electrodes are also used. So how you do the data acquisition in case of a CV? So here I'll show you one voltammogram. This is a voltammogram of a bare electrode under nitrogen. So you don't see anything over here, no oxidation peak, no reduction peak. This is a bare electrode under air. You see definitely one oxidation and a reduction peak over here. And then when you're using this particular compound over here, you see this green line which you see is under nitrogen, and you see this well-defined oxidation and the reduction peaks. Whereas if you use the same material under air, you see this peak is looking very different. So what it shows is that nitrogen is electrochemically inert within the window, but oxygen is definitely reacting, because you can see this oxygen, it is showing an oxidation reduction. So it is again reacting with your particular material, and this. So that is why you have to be very careful about the atmosphere you are using. Whenever you are using these three electrode materials, then you have to be very careful about all these data acquisition procedures. And of course this is something which is for to take care of less amount of electrolyte should it shouldn't be bubbling out, or vapors shouldn't be produced in the solvent of the electrochemical cell, so you use a pre-bubbler. So these are all the steps for the data acquisition. Now you have something which is known as the open circuit potential. So when a cell is assembled, the analyte has been added, the potential will develop at the electrode. So the potential which is observed when no current is flowing is called the open circuit potential, or OCP. And this is going to give you information about the redox state of the species in the bulk solution, as well as the concentration of different species when the solution contains a mixture. So now what you have is, you will find that whenever you are doing these kind of, you're making these kind of electrodes, or you're making this kind of cells, three electrode material, or for that matter your cell, there is something which is known as ohmic drop which happens. So why these electrolyte solutions, they have an intrinsic resistance in the electrochemical cell. So there is going to be a kind of a resistance for which there is going to be a kind of a drop. So this V is equal to IR. So you see, what you see is there's going to be a resistance drop over here. So while some potentiostats, they compensate for most of the solution resistance, there remains a form of this, uncompensated resistance between the working electrode and the counter electrode. So what happens, how do you know that there is an ohmic drop happening? Because you will see this peak to peak separation in the voltammogram for an event which you know is actually electrochemically reversible. So how do you mitigate this? So you can do this by reducing the size of the working electrode, or restricting the experiment to very slow scan rate, or you can decrease this thing by increasing the conductivity of a solution by using very high electrolyte concentrations, or you can diminish the distance separating the reference electrode and the working electrode. So by this you can minimize this peak to peak separation. So what is the advantages of CV? So you know whether the chemical reaction of the reactants is reversible or reversible. The potential at which the oxidation or reduction occurs, you can determine that. Quantitative analysis also possible, and it is also possible to measure by changing the test conditions such as scan rate, temperature, and concentration of reactions, various other factors. So equations of voltammetry for intercalation system. Now this is very important. This is where all this was the preamble. So now where do you use CV in your battery systems or your coin cells? So in a reversible process, please understand that the rate of electron transfer is rapid enough at the surface of the electrode, and the peak potential is independent on the variation of the scan rate. So it should be this. Whereas if it is a quasi-reversible process, which show limitation of electron transfer kinetics, the peak potential will become a function of the scan rate. So if it is reversible, it is independent of the scan rate. If it is quasi-reversible, then it depends on the scan rate. Now understand this lithium intercalation reaction, which is what we see in LIBs, they follow a quasi-reversible process. And that is why the cathodic and anodic peaks, they are dependent on the scan rate. So to obtain exact lithium ion diffusivity, two boundary conditions should be considered according to the scan rate. So if you have a semi-infinite diffusion process, which is a fast scan rate, this is going to be the equation where your IP is basically dependent on the square root of your scan rate. Whereas if you have a finite diffusion process, which is a very slow scan rate, in that case, what is happening? This IP is directly proportional to your scan rate. So considering the different diffusion behaviors induced by the scan rate, this is the final equation which you have. So this here you can see this IP value, and this is where this beta, the beta value, whatever is given over here, this is having this scan rate value, and this is the actual equation which is used for getting the current value as per your scan rate. So now what we do to find out the lithium ion diffusivity using cyclic voltammetry technique in lithium ion battery is this sweep rate voltammetry technique. So in a battery system, the electrochemical reactions, they occur in the electrode through consecutive processes. So the current is going to obey the power law. So I is equal to A nu to the power of B. So I is the current, this nu is the scan rate, and A and B, these are adjustable values. So now this B value is the sum of the diffusion control, which is Faradaic process, and non-Faradaic or capacitive currents. So if only diffusion control reaction is there, then this observed current is going to be proportional to the square root of your scan rate according to the Randall-Sevick equation. Whereas the capacitive current, which is also known as the non-Faradaic or double layer current, this is going to be directly proportional to the scan rate. So please understand this, all these different equations, that is just to give you a flavor of it. But otherwise, what is this is the capacitive current is dominantly measured at a fast scan rate. So when you're doing a very fast scanning, you are actually finding out what is the capacitive current, and the diffusion controlled current you will dominantly measure at a slow scan rate. So that is why you are changing the scan rate and you are recording your CV for a lithium ion cell. So the B value of total electrochemical reaction is composed of both this. So you have both diffusion control and you also have capacitive control. So if you have values which is between 0 to 0.5, it is diffusion controlled. And if you have values which is between 0.5 to 1, then it is known as capacitive control. And if you have any values between that, then it is both diffusion as well as capacitive control. So what you do is you are plotting this log I and log mu, and you are getting this particular straight line, and the slope is going to give you this B value over here. So now the total current, how we will get? The total current is I is equal to K1 nu plus K2 nu to the power half, because this is basically your capacitive current and the other is your diffusive current. And now from this slope value, you will make this particular plot over here. You can see this is scan rate versus this I nu to the power minus half. So you are plotting this versus this. And from this slope, you are getting the K1 value. And if you are putting the K1 value in this particular equation, you will also get the K2 value. And so you will get how much of the current is attributed to capacitive reaction and how much of the current is attributed to your diffusion control reaction. So this is basically the idea of your current which is coming in from the various scan rate when you are scanning when you're doing recording CV of your lithium ion coin cell. Now, how do you get the kinetics of this electrochemical reaction? How will you get the diffusive value? So for that, you have this particular reaction. Please understand this. This is that slope value, whatever you got from the previous reaction, divided by this value and multiplied by RT by NF. And so this particular equation is only valid when the phase does not undergo any phase transformation during lithiation and delithiation process. So it is only a single phase diffusion, not a multi-phase diffusion. So this is an approximation which I have to use. So when I'm doing an intercalation reaction, I can find out the diffusion coefficient through my CV, provided it is a single phase diffusion and it is not a multi-phase diffusion reaction. And you can also determine the specific capacity by voltammetry. So for that, when calculating the charge storage in a cyclic voltammogram with an asymmetric shape of the cathodic and anodic peaks, it is usually possible to obtain the integrated area of the cyclic voltammogram. So you have this pura area which is coming in, and then how you will get the specific capacity? You will multiply it with your delta U value. And so this Q value is given by this particular equation. Okay, so this is how you will determine your diffusion coefficient as well as the specific capacity using CV techniques for a lithium ion cell. Now you look how this, with the scan rate, how the CV pattern is changing. So the red one is for your lowest scan rate, whereas for the highest scan rate, you see the current is value is increasing. As I said, why? Because that time more and more current is passing, which we had already explained in the previous slide, why you will see more current when the scan rate is much higher, because there's going to be a faster charge discharge over here. So what is happening? Here what you are having in this LiFePO4. In one case you have taken nanoplates, in the other case you have taken microplates. So what you are seeing, that when you are having a size reduction, it induces an increase in the interfacial area in the particles. That is, the contact area with electrolyte is increasing, and it is shortening the diffusion length of lithium ion. So as a result, what is happening? There is enhancement in kinetics of redox reaction, and the overall peak current increases at the same scan rate in the cyclic voltammogram. So you see over here at 2 millivolts per second scan rate, the current is more than 0.004 amperes over here, whereas in this case it is less than 0.004 amperes. So with a nano plate, the current rate is increasing. So this is the factors which affect the shape of voltammetric curves. Then electrode thickness. If you have a thick electrode, the scan rate increase shows larger peak split. You can see the difference. Peak split is this delta EP value compared to the thin electrode, which is on the top. This is a thin electrode because the distance is 0.11 micrometer, whereas in this case it is 4.2 micrometers. So what you see over here for the thick electrodes, with the increase in the scan rate, it is going to show a larger peak split compared to the thin electrode. Why? Because the lithium ion diffusion from the surface to the bulk is becoming more difficult. So the bulk potential of the electrode, it depends on distance from the surface, and this is going to cause the potential drop. So this is how, again, the electrode thickness is going to affect how your CV curve is going to be. Then temperature. So peak current which arises from a diffusion control reaction is significantly affected by your operating temperature. So if you look into this particular CV plot over here, this is corresponding to 30 degrees centigrade, and the solid line is corresponding to 50 degrees centigrade. So you see the rate of the electrochemical reaction depends on lithium ion diffusion in the lattice of the active materials, and this diffusion process is temperature sensitive. When the peak split decreases at high temperature, it indicates that the rate of electrochemical reaction becomes faster, and the corresponding redox peaks are also appearing earlier. So over here you see that there is a shift in this peak, whereas over here you see the peak is shifting over here. So this is how basically temperature is again affecting your voltammetric CV curves. So now we come to a few definitions. So one is terminal voltage. What is terminal voltage? Terminal voltage is the voltage between battery terminals when you are having a load applied to it. What is open circuit voltage? Voltage between the battery terminals when there is no load applied. So when I say open circuit, no load. When I say terminal voltage, there is a load. Then there is something which is known as internal resistance. So this is what? This is overall resistance within the battery, which varies with charge level and temperature, and generally it differs with charging or discharging. So to what extent it is getting discharged, to what extent it is charged, it's also going to change the extent of the internal resistance which is felt by the battery. So as the internal resistance increases, please understand the battery efficiency decreases. And this extra charging energy, what happens now? You need to put in more energy to charge the battery. This extra charging energy is converted to heat. So this is the reason why we say that if there is a high resistance, why the battery gets heated up. Battery capacity is the amount of electric charge it can store in a specific condition. It is measured by discharging a fully charged battery through a load at a constant current rate. So you see the capacity of a battery. This is given by this particular equation, where it is a function of IDT, and this is being integrated from your minimum voltage to the maximum voltage. So capacity of a battery, this depends on the discharge condition, discharging current rate, temperature, etc. Okay. So now, as I said, now we will talk about a little charge and discharge testing. So what is happening? You just see over here, this is a typical charge discharge curve of a coin cell. So this is the charge which is given in green. We are charging the battery, and this is the discharge which is given in blue. So when you charge, it looks like this. When you discharge, it is coming down like this. Okay, so this is the charge and discharge. So voltage, if you see, it increases steadily while charging the battery. During this step, the lithium ions, what is happening? It is extracted from the cathode and it gets intercalated into the anode graphitic layers. Okay. And so then what is happening? The cell, this will now be held potentiostatically at 4.2 volts. Why? Because 4.2 volts is that for the cathode. Okay, this is the upper voltage limit. And then what is going to happen is this step is going to last for some time, and this is basically corresponding to a C rate. C rate is what? C rate is basically how fast you are charging and discharging a battery. So this is going to ensure that the battery is fully charged. So the battery state of charge now here is around 100%. The voltage initially drops at the beginning of discharge. So the moment you start discharging, you see over here what is happening. This voltage which was over here, there is going to be a drop in the voltage the moment you start discharging. So according to Ohm's law, this voltage drop or delta U, this is directly proportional to the equivalent series resistance. So delta U is I into equivalent series resistance. And so now what you have over here is this equivalent series resistance is the sum up of resistance from the electrodes, electrolyte, and all the electrical contacts which are there. So the lower the voltage drop delta U, the higher is the maximum output energy E that can be drawn from the battery. So whenever you make this electrode, electrolyte, and electrical contacts, your aim should be that how much less of voltage drop you can get over here. And the limit of a battery's usable capacity is reached when the voltage declines sharply. Okay, so the discharge step is stopped at 2.75 volt in this particular case. So you see this voltage is dropping sharply. So at this potential, the state of charge is defined to be 0% and the depth of discharge over here is 100%. So I was talking about the C rate. This described how fast a battery is charged or discharged, and the batteries used for this application have a rated capacity Q of 40 milliampere hours for a 0.2 C rate. So this means that ideally what you can draw is 8 milliamperes for 5 hours according to this particular equation. So please remember, this is how you can change the C rate and you can change the amount of current which you can draw from your battery. So what we do in case of a battery material, we keep on charging and discharging it. And so you see that when you are having these various C rates, when the C rate is low, the capacity is going to be very high. When your C rate is increasing, the capacity is going to get a little lower. Why? Because the entire amount of lithium is not able to get back to your cathode and again move back into the anode. So that is why your specific capacity kinds of falls. So what we have to see is for a particular C rate, how the cycling is happening. So how your charge discharge cycle is moving. So this has to be as flat as possible to ensure that whatever is going in, lithium ion is going in, the same amount is coming out. So batteries are charged and discharged for several hundreds of times and this capacity is measured. So this is battery cycling. And with this, I come to an end with today's lecture. If there is any question, you can please ask me. So if there is no further question, then we sign off.